All right, we'll get started. Thanks everyone for coming. If you're on Zoom, hopefully you can hear us. If not, complain to Jake. We're delighted to have Conrad Tucker, who's from Carnegie Mellon University, and where he is the Arthur Hammerschlag Career Development Professor, which means that he makes $1 million. So he's in the mechanical engineering department and has also an appointment in the machine learning department at CMU. And we're delighted to hear what he has to tell us about artificial intelligence and its impact on engineering, design, and manufacturing.
All right, thank you very much, Jamal, and thanks for the invitation. Thanks, students, for coming, faculty, researchers, whoever's here in person and online. I'm going to try to make this as interactive as possible and leave plenty of time at the end for Q&A. So the main aspects of this talk are going to focus on the engineering design process. And for some reason, this isn't working. Okay, there we go. So the three main components of this talk are, the central theme is artificial intelligence, but I'm going to show how it applies to engineering design as a generative tool, as a systems controller. So once you've designed your system, and then finally, how artificial intelligence can be used to protect the state, the operational state of the system that you design. So if we start off with artificial intelligence as a generative tool, let's take a step back and really just summarize the engineering design process. So how many of you have heard of the engineering design process or familiar? Okay, so if you think of the engineering design process, it's the standard process in which most things that we enjoy today get made, whether or not it's a chair that you're sitting on, an aircraft or an automobile. It follows these steps in an iterative manner. And really the focus of today's talk is going to focus on the ability of AI to help accelerate the speed at which we can actually generate ideas or concepts. So early stage conceptual design. So I'm going to pose a question. This is going to be my first of many quizzes to the audience. Please feel free to just yell out. If I showed you these three objects and asked, what do they have in common? You can't, Jamal's not allowed to answer yet. What do you think? Yeah.
So it have to fit the user need.
Okay, user need. Any other ideas? They seem completely disconnected, right? A ring, a large commercial aircraft, and a coffee mug. Well, it turns out that these and many other products are designed using computer-aided design tools. How many of you have used a CAD tool to design stuff? Okay, so if you have, maybe you've designed something like this for yourself, or you've seen this process of designing. So if we actually look at how this works, there are many tools out there that are very parametric in nature. So I remember going through and learning some of these tools as a painstaking effort of learning what each of the functionality of the tool is, so that you can learn to create a wide range of different geometries, ranging from components all the way to systems that are then integrated. So if you think of what the surface is, or what this geometry is, if we zoom in, you can think of a surface as being made of a collection of triangles. This is just one type of representation of what you see here as that 3D model. And if we delve even deeper, you can think of these triangles as being a collection of points that are linked by edges. And so really what the first aspect of this talk is going to show is that we are at the stage now where we're able to have AI learn how to take these collection of 3D points in space and organize them in ways that look like something that a human designer would create. So as a sanity check, when you see this, what does it look like in the end?
Plane.
Okay, looks like a plane, right? So what are the visual characteristics that make something look like a plane is one of the questions that this algorithm like this would be trying to solve. And really what has spurred this advancement in this field are a new class of neural networks called generative neural networks. There are actually two networks together that are solving a minimax optimization problem. The one network is called the generator network. You can think of this as the designer, the idea generator in terms of analog of a human. The other network is the discriminator network. You can think of that as the critique of whatever the generator comes up with. So in mathematical terms, the generator has a vector of dimension, a z-dimensional vector, and it tries to come up with a sample G of Z that when shown to this discriminator, the discriminator thinks that the sample is drawn from the same distribution that it was trained on. So let's give an example. A real world example, I'm going to pose it back to you just to drive home this point. I'm going to start off with something very simple. If I asked you what this is, you would say, let's all the way in the back.
Apple.
It's an apple. Does anyone have any other definition of what this is? Okay, so if it's an apple, what happens if you try to reach out and try to grab and bite the apple?
Grab it.
You cannot grab it. So is it an apple? We have to be more literal, right? We're dealing with computers. Yes?
It's a visual representation of an apple.
It's a pictorial representation. So very important distinction because this is a two-dimensional representation, lacks texture, it lacks taste, it lacks many other features that this does not have, right? So if you're training a neural network, you have to represent your data space in this very literal and explicit way, okay? Let's start with, let's go on with another more difficult. What is this? Who haven't we heard from? What do you think this is?
Picture representation of banana.
Picture of a banana. Any other thoughts or ideas? Everyone picture of a banana? Okay. What you just did, this process, and I don't have a backup plan if you did not think it's a banana, but you served as a discriminator and as a generator. And actually, this is not a picture of a banana, it's a picture of a plantain. So very feature-wise, they look quite similar. So you can think of what just happened as a generator showing you a data representation that fooled you into thinking that it was drawn from the same distribution of all the bananas you've seen before. And if you tie this back to the generative neural network, the discriminator is the classifier, the generator is tasked with coming up with data representations that fool the discriminator. Okay, so they're playing this game of sequential learning. So how does this apply to the process to create this, right? So who wants to give some ideas? How can we take that idea that we just talked about in, what do you think? Red shirt.
Is that got an algorithm trying to arrange the points in a way that the discriminator algorithm think looks like a plane?
Yes, right? So you can think of the generator starting off not very good, right? It shows the discriminator an apple. And of course, that doesn't look like a banana. And over time, the generator learns to approximate the distribution of something that looks like a banana, or what the discriminator would be fooled to think that it's drawn from the same distribution as its own training set. So this is the paper that we published recently that's taking this generative neural network idea and applying it to the problem of engineering design, specifically early stage conceptual design. So you take a collection of points, you first train this discriminator as a classifier so it learns what planes look like. So you have a diversity of points that look like planes, and then you have your generator learn to approximate what that distribution looks like. And so what would be the point of this? Once you have trained the generator, you can start to extrapolate and come up with new designs that still look like planes, but may not necessarily look like the typical plane that you've seen. And we'll look at examples of what that looks like. Okay, so if we dig deep into, well, how is this data represented? You can think of each of these points as existing in a three-dimensional space, just an XYZ coordinate. And then for this specific training model, we have 2,500 points, but it's not limited to 2,500 points. Now, one of the challenges of training a neural network on a point cloud is that there's spatial information that is represented or embedded in this collection of points. And somehow you have to convey that spatial representation to this classifier. So your original 2,500 by 3 collection of points is transformed into a 1 by 1024 vector. You can think of that as encoding the spatial characteristics of this point distribution. And the discriminator has a job of seeing if this came from the same distribution as its training data set. So it's primarily a classifier. So once it's trained, anything that looks kind of like a plane from its training set will be classified as, yes, this is a true plane. Anything else is considered not a plane. Okay, so that's the discriminator network. The generator starts with a lower dimensional vector, in this case, 100-dimensional vector. And you can think of these as the knobs that are tuned in a nonlinear way to take this 100-dimensional vector and come up with a point cloud distribution of 2,500 by 3. So you tune these knobs in order to learn the distribution of points that would fool the discriminator into classifying. So if you tie this all together, what is learned by this feeds into the discriminator network, and you do this in an iterative manner. So what does the output look like? What you're seeing here is a fully neural network designed geometry of something that looks like an aircraft. Of course, you can see some imperfections in the geometry, but keep in mind, this neural network has no concept of the physical principles of lift or force that have enabled it to come up with this design. And once you have this trained network, you can actually perturb this space to come up with a wide range of different geometries. Furthermore, if you train this on multiple classes, you can start to do some type of extrapolation or combination of different classes that you come up with something that is a hybrid of a car and a boat, or there are a wide range of things you can start doing. And so now you have a neural network that is accelerating the speed in which design concepts can be generated, so that you could possibly come up with new ideas that a human designer may not have considered as it pertains to an aircraft or a watercraft or an automobile. Now, of course, one of the beauties of this is that the native format of this output, I actually have a model, the actual 3D printed model of this. You can actually send this directly to a 3D printed machine to have your AI designed system to actually be realized in physical form. So now you start seeing this end-to-end process of AI generation and machine realization in this 3D printed form. But as we all know, this is not how most systems are. Most systems, when we think of manufacturing, it's actually mostly assembly. You have components or subsystems that then come together. So if that's the case, if demonstrated that we are able to generate entire geometries, then all you have to do now is decompose this aircraft into different parts using a similar kind of idea where you can generate a wide range of different objects and geometries. It really allows a very nice exploration of your design space. So you start coming up with these different designs. And then now the goal is, if I have these different components, in the same way that you have an aircraft manufacturer put these things together, this becomes a control problem. I have the system, I want it to do something. How do I have a neural network not only learn how to create these components, but actually assemble them and functionally use them in ways that achieve some function? So this is the second part of my talk of AI as a systems controller. You've generated the system. That's, in this case, a 3D representation of that system. And now you want to see how to put these components together. If that were the case for your chairs that you're sitting on, the bottom part of the chair that flaps could be one system, the back is another system. The AI learns how to put these together to create this fully functional chair. So imagine taking that one piece that you put together, and when you join these together, well, you start having something that has an emergent property like a rotor, which can create lift. So not only are artificial intelligence algorithms able to create geometries, you can start having them learn how to use things. And then you have this nice feedback loop of a neural network as a designer of geometries and another neural network as a evaluator of what has been put together that achieves a particular function. So how many people have flown a drone before? Quadcopter, drone, tricopter? No one? Okay. So if you haven't, flying a quadcopter is much easier to learn than a tricopter, just because of the spatial positions of the rotors and achieving stability when you're flying. So the task of this neural network, without ever learning what these things are, imagine it's just components, is to take this drone design and learn how to apply certain rotations to each of the thrusts. So this becomes a reinforcement learning problem where your environment is whatever simulation environment that you have. And the state representation is you're giving a task of, let's say, hovering to this red ball. Your action vector are the thrusts of each of these rotors. And these are the representation of the state space. All right, let's take a look at what this looks like. So who thinks this is good? Did you do better if you were learning to fly a quadcopter? Maybe this is a very low baseline. So this is initialization of this neural reinforcement learning agent, a deep learning reinforcement learning agent, where it's trying to learn what these things do. I mean, it shouldn't be surprising. If I gave you something that you had no idea what it is, it's trial and error. But what's interesting is that over time, and this is about 2 hours or so of training, this neural network that was given these components to apply some action to learned how to evenly apply forces to these rotors in order to achieve this stable flight. What's even more impressive is the transferability of this. Remember, I started off by telling you that it's much harder to train a tricopter than a quadcopter because it's very difficult to fly. So applying the learn model of your quadcopter to this tricopter design, you can see that it becomes a hard problem as well. And over time, the neural network is able to learn how to control this tricopter in a stable way. What's more fascinating is that if the neural network started off by trying to learn this tricopter design from scratch, it never converged to any feasible solution. So we're demonstrating transfer learning, which is from this paper that we had of, it's almost like curriculum learning. So teaching a network an easier task and then having that translate to a more difficult task that was then successful. This is our ultimate goal. We're not there yet, but imagine now you're able to transfer knowledge from a simulation and actually put this in a real world controller of a real world system. And imagine what the capabilities that would do in terms of expanding. Right now, the control mechanisms for, let's say, this quadcopter are based on a human designer that has encoded that these rotors could spin at the same RPM, for example. Well, imagine you took the trained weights from the simulation and you're now able to apply it to a real world problem. This has the potential to democratize not only design, but controllers, because let's say you come up with a new configuration for a quadcopter or a drone, you would have to wait until there's a control algorithm to be able to control it, as opposed to having a neural network learn a control algorithm that would be suitable for solving this problem. Yes.
Question. So it's actually very fascinating. So on the other, you were explaining that if you did this with the tricopter instead of the quadcopter, you wouldn't be able to learn. So I wonder, instead of forcing it to be a tricopter or a quadcopter, you gave it the option, the choice, and you sort of randomized. You can either use 3 or 4 pieces if you want, but you're not required to use all 4. You're not required to use all 3. Does that sort of help, I guess?
So that's a great question, and we actually tried that. We enhanced the complexity of this problem. So what we first did was enable the neural network to decide how many rotors to use, and also the location of the rotors. And it did come up with feasible solutions for achieving this flight in simulation. The challenge was, and this is where the human intuition comes. Let's say you have a neural network that comes up with a 7-rotor solution. It's a feasible solution, but it's not an efficient solution. So how do you embed the concept of efficiency into this process is something that we found quite challenging. So yes, the neural network was able to come up with other types of designs and solutions, but it then became a challenge of how do you craft the right reward function in order to achieve efficiency. Let's say you go with 2 rotors or 1 rotor. That's really where the open question is.
I have a question.
Yes.
Why don't we complicate the reward function? So make the reward function the reward of achieving a certain height for a feasible solution. It would be say an integer plus integer. But if the agent was able to achieve that height with minimum number of rotors activated, the reward will be integer plus n, and this will probably try to minimize number of. It will increase efficiency, correct?
Right. So if you think of some of the challenges of design as a whole, if you look at the entire design space of most problems, there are magnitudes more ways of doing something wrong than there are doing something right. And what then happens is that you have this class imbalance distribution of filled examples versus feasible solutions. And we actually tried kind of incentivizing the reward function just based on what you described. And some of the challenges that we found were the instantiation of where the search space starts, and just getting feasible solutions that were consistent and being optimal, because you do have multiple objectives. If we look at the states, you have the drone's position, you have velocity, acceleration. Depending on how you craft the reward function, some solutions were the drone never got off the ground because there is a penalty of, let's say, having impact. So what's one way to have minimize impact is to never to do anything. So yeah, those are some of the challenges in crafting this optimal reward function, and those are some issues that we're trying to move beyond right now.
One other question is, okay, like a tricopter just seems silly because if one of the rotors were to fail, it doesn't seem like you would recover really.
Okay.
And so can you make these designs so that if a part or two parts kind of fail, doesn't matter where they are, like you can still kind of achieve this like recovery?
Right. So I think if you, and this goes to the action space again. So right now, the action space was the determining where these rotors are and also the thrusts for each of those rotors. What you just added was, can I also alter the position of those rotors to accommodate for some type of failure event? That significantly expands the action space, which then increases the complexity of the problem. So the more we work on these problems, the more you have a deeper appreciation of the human domain knowledge. I think when you think of the impact of how AI is going to complement humans, it's maybe coming up with efficient simulation or solving, but it's not the domain knowledge that would help you realize that putting a rotor in one place is better. I think humans have a good way of filtering out bad solutions rather than trying all these solutions. But it would be great if you could have like a real-time adaptive system where if this rotor fails, these other ones are able to slide and move to different positions. But then you either are having a continuous action space of the position that would need to slide to, or you discretize that action space, but still, it's still a very, you've increased the complexity of the problem. So there's still lots of opportunity. Another challenge here is the representation of physical controllers isn't a one-to-one mapping. So for neural network architecture and simulation, doesn't just map nicely where you could just download this into a traditional physical controller and have this the state action representation like a physical system. So this may help inform or motivate human designers in coming up with a more general way of making physical controllers that could either have a human created controller or a trained neural network controller that then transfers to this physical system. Okay. Finally, I'm going to show AI as a systems defender. You can think of what motivated this part of our research is if you've spent all this time coming up with this physical system, you do not want other externalities altering the state of the system in ways that you did not intend, right? So if you're a systems engineer, then you are undoubtedly also concerned about maintaining the integrity of the system that you've created. And this is where this last part comes out. And this threat that I'm going to talk about comes from the most unpredictable area. Now, why would the Deputy Director of the Air Force think that social media is one of the largest vulnerabilities to the Air Force mission, or cybersecurity as a whole? What are some thoughts from the audience?
Well, because it can have like an agent who actually able to produce certain text or media that can move many mass of people to do a certain action. That's one.
Right. So now we live in a world where the digital space can actually impact the physical space. If you think of the vulnerabilities of our interconnected society, you have human to human communication, you have human to machine, and you have machine to machine. When you think of cybersecurity, typically, we think of some malware impacting another machine, but actually the information that is communicated to a person can also be considered malware. And then what that person does in the physical world could have devastating impacts on your physical system that you spent so much time and resources creating. So if we look at social media as a network of nodes and edges, the connections between people, what we really are trying to do is minimize the vulnerabilities of the human network that may then compromise or potentially risk compromising the man-made systems that we've created. So trying to mitigate these challenges in the digital space so they don't adversely affect the physical space. Here's what should be concerning to you. When COVID first was launched, I don't know if you saw this, where there was a conspiracy theory going on in social media that 5G networks cause COVID. You guys didn't know that 5G networks cause COVID? Did you know? Yeah, they do, apparently. So you can see the spike in the posts pertaining to 5G networks and COVID. I mean, really astronomical difference. Not only links, but photos and videos that are trying to confirm the existence of this, this link. Now, imagine you have this large-scale network coupled with your misinformation that's propagated, coupled with the advent of AI-driven deepfakes. So this is my student on the left that is doing this enactment using still pictures in the middle that's able to animate these videos on the right. And this is publicly available on GitHub. This the paper is First Order Motion. You can find it on GitHub. Any of you could download this. It's not our work. It's an algorithm that from the CS department. We just used it in a recently NSF-funded study to demonstrate its potential impact in our society. So imagine now you have President Biden being animated and given this public state announcement of 5G networks causing COVID, and that's being shared on social media. And by the way, the actor is a grad student that's just doing this. By the way, we did not do that. I'm just demonstrating what the risk is. And if you think of social media also as a network, you start to have this information propagation that we're trying to mitigate, the misinformation propagation. Why is that? Because it actually could have real world effects. So this is a recent study in the UK of people actually going to destroy these 5G networks. It's not just for laughs. Like these cyber or conspiracy theories can actually have real world impact. So to the point where Twitter had to start banning posts that dealt with 5G and COVID because people were actually destroying these networks. So if you were a scientist, because this is part of our job as engineers, and let me hear from the audience, how would you communicate to the average person that this link doesn't exist? What's going on? What's the issue here that people are relating COVID and 5G networks? What's the error in their thought process? Yes.
Confusing correlation with the causation of these events.
Correlation and causation, right? 5G networks typically found in cities. Cities typically have a denser population. With denser population comes the increased ability to transmit airborne diseases like COVID, right? You could falsify this hypothesis by going to places that either don't have 5G to see if COVID exists. And I mean, there are many ways you could, but it's fighting against this critical mass of misinformation that then have real world impacts on your system. So that's what we're trying to avoid. So if you model this kind of human to human vulnerability or human to machine as some type of graph, what you want to do is quantify the relationships between people. So you can think of each of these nodes being a person, and the links being the relationship that these individuals have with other people. So now, using kind of like this graphical neural network approach, you can look at the topology of your network and how the topology changes as you inject misinformation in. So if I injected misinformation into node 3, that's shared to node 2, and that's shared to node 7. You could see that propagate like a wildfire. And what you're then able to do is make an inference of whether or not this propagation is carrying misinformation or not, based on the manner in which the information spreads. So you can think of this. So this is an algorithm that we came up with, where you're looking at the distribution. We quantified information in an entropy manner, and you can look at the distribution of entropy pertaining to fake content and real content and seeing if they're different. And if these distributions are different, then you can use this as a classifier without even knowing the content of the information. You can just look at the way the topology of your graph changes as different types of information spread. So to just kind of tie things together, AI has tremendous potential in the engineering design space. I showed that we can use AI for to generate 3D concepts. You could also use AI for controlling systems once they have been created. But once you have created a system, now you have to protect the system so that it operates in a manner that is consistent with its intention. And so these are the 3 ways that we have used AI in our line of research. And when I say we, this is a larger effort that I like to acknowledge my entire lab and collaborators and many funding agencies that have funded different components of this work. Can anyone spot out who the deepfake actor was in the lab?
Was it Mitch?
Mitch is our great deepfake actor, and he's a great sport about it. But any of you can download these algorithms and try it out yourself. So with that, I'd like to thank you for attending and open up to any questions that you may have. Thanks.
Thank you. I have a question. So,
Yes.
So for the slide before this, where the algorithm that you guys put together, and basically look at the distribution of the entropy between a normal behavior, a message, say, and a message that it can be fake or it can be destructive. But does this hold also like when it deals with celebrity? They tend to say controversial things to continue draw attention to themselves, and that's how they actually make living. Does this algorithm discriminate against this kind of behavior of celebrities?
That's a good question. Let me go back to. So the short answer is yes, and it's based on the architecture of the social network. I try to draw parallels between social network as some type of neural network. If you think of what a neural network is, it's a message passing system that with votes, right? So each node votes on information that was received, and then it gets aggregated in some way, and you have a classification. Rather than focusing on one individual in this entire network, you can think of our approach looking at how the information propagates as the predictor. So if you think of this first node here as a source, let's say the celebrity, we're not going to focus on just one individual. First of all, it's risky if that person's account gets compromised, but it's also not scalable, and it's difficult to just focus on one. So instead, we look at the topology, the way that the information propagates, and make an inference without having to know what the information itself is. I guess the hypothesis is there's a difference in the way that misinformation propagates through a graph and the way that true information propagates. That's the central hypothesis. So if that's the case, then all you have to do is come up with a way to model the way that this misinformation spreads, and then use that as a way to serve as a classifier. And that's what this algorithm does. How people like information, how they share information, and their connections are all used to make an inference of, is this fake or authentic information? Any other questions? Yeah.
So that works. Oh, go ahead. Sorry.
So for using AI as a generative design tool, there's a lot of, I guess, for the example of an aircraft, there might be a lot of analysis that goes into what geometries are appropriate for providing certain lifts. Is there any application of artificial intelligence for sort of coupling the evaluation of those designs that are generated?
Yeah, so you're now describing our most recent work, where we are going beyond just the geometric representation of a design to actually trying to encode neural networks with a fundamental understanding of the physical laws that govern the world, like the difference in the velocity or pressures that create lift in the first place. Because if you can understand that level of fundamentals, then you're moving beyond just a correlation of, well, this looks like an aircraft, therefore it has lift, to this type of topology of this geometry is what creates this pressure difference that creates the lift. So that's where we're going.
I guess just as a follow-up question, I'm curious, how computationally expensive is the generation of the geometry compared to the evaluation of it?
So the evaluation definitely is more computationally expensive because you have to wait. I guess it depends on what it is that you're trying to evaluate. But for multi-function types of artifacts like an aircraft, you're not only evaluating lift, you're evaluating efficiency. So there are many aspects that make it very computationally more challenging than just the generative component. One of the great things of simulation, though, is now you can, I should have emphasized this in these slides, you can parallelize, so you can think of each of these red balls as its own neural network learning. And then you can pull that knowledge from these multiple instantiations of the network. So in essence, you're accelerating the knowledge. Imagine if we can do that for people, where each of what you've learned can be pulled together for this kind of collective, I guess that's what the internet is supposed to be, or I guess it is in some way. But yeah, that's how we can accelerate the speed of training is to parallelize. Yeah.
I have a quick question. The generative tool for geometry design, does it have anything to do with something called topology optimization? Because I know some people from like this field, they also focus on designing new geometry that have certain functions.
Yes.
That seems your goals are the same, but
yeah. So topology optimization is a well-established field, very active. You can think of it as trying to achieve similar types of capability. I think one of the main differentiators is that we're trying to reduce the amount of domain knowledge that's needed to achieve these capabilities. So topology optimization brings with it a lot of domain expertise of how to set up this problem. When you look at the neural network representation, all you're giving this model is a collection of points that it has to learn what organization of points would be classified as a particular system. So you're really reducing the amount of domain knowledge that's needed to optimize or come up with these new designs. Yes.
One thought is with sort of these like deep fakes, I feel like they actually, like we view it as negative, but I could view it in a positive way. So suppose I want to communicate, calculus to a class. If I get up there and do a calculus lecture, like let's say via Zoom, so we can pretend that I'm there, it's very differently received than if, I don't know, let's say Will Smith does the same lecture on calculus, and I actually think the students might learn more if seeing him than versus seeing me. I mean, I'm cool, but I'm not that cool, right? So
yeah, I think you're pretty cool.
But
no, that's a good point. Yeah.
So how can we leverage that actually to? I don't want to replace myself, but
right.
Like, how can you replace the boring professors with exciting people, yet still sharing the same content?
So I think you open up, pose a very interesting question that we should consider as academics. What is the future of our objective is really to optimize the efficiency in which students are acquiring information, right? Knowledge. And if that means you have a celebrity deliver that content that maybe that, I don't know what the model of that would, if Will Smith would get royalties every time.
I get the royalty.
Or you get the royalty. So, but this opens up very interesting questions of assignment of credit. The statue is I mean, all of these are animated from just a single picture, right? What does it mean if these are in public domain? Would you right now? This is possible that I could take you. I should have done this. Taking your website picture to have you on here to animate. What does that mean for access or control of our beings? Would you be cool if you turn on the TV tomorrow and you're giving some guest lectures halfway across the world and you had no idea about it because someone was using this to impart knowledge? These are all questions I think we should be asking from a societal perspective. So I think it's a double-edged sword. I think there's tremendous opportunity to do good and to accelerate maybe access, but also just highlighting the potential ways that this could be exploited in ways that are detrimental to society. So.
All right, there was one last question online, and then we'll conclude.
Yes, one last question. I'm sorry. What software you use for the simulating the environment? Is it Blender or is it AutoCAD? Or I'm just curious to know.
Yeah, that's a good question. This in the middle here is Unity, the Unity gaming engine. It's interesting that many of these gaming engines started off for video games, but now they're going into AI and physics-based simulations. There are many other, we're not unique to this platform, but this was nice because it has a Python plugin that you can connect and train your neural networks offline and then bring directly back to the platform. So it does have its limitation that the actual physical modeling isn't as high fidelity as, let's say, a Fluent or these kind of more expensive, which speaks to your question earlier about what is the computation time. It depends on the accuracy that you're trying to attain, right? If you just want a quick, rough approximation of error characteristics, maybe something not as high fidelity. But if you want something more precision, this may increase your computational costs.
I'm sorry, one last question. I'm very annoying. Have you guys tried basically the AI as a generative design tool that's linked in serial as the system controller?
Serial. I think I showed a picture earlier.
Well, basically the controller as an algorithm that can refine the design output.
Yes. Yes. So we have this loop, and it's, if you really think, it's a very difficult problem about the chicken or the egg.
Yeah.
Let's say you have a solution that the AI controller was unable to achieve a functionality. Is that because the design was bad, or is it a function of the controller? If I give a car to a 5-year-old and they crash it, is it the design of the car that's bad, or is it the controller? And really, we don't have. It's a difficult question to ask. Yes, you could start off with a professional driver, but how do they attain their expertise? Is by driving things that were similar in the past. So you've already biased the expert by the time they are introduced to a new design. Does that make sense?
Makes sense.
Yeah, this chicken or the egg problem.
Thank you so much.
Yep. All right, let's thank Conrad.
Thank you very much.